Hello, everyone. Today I will be discussing an exciting topic in quantum science and engineering the applications of nitrogen vacancy, otherwise known as MV, centers in diamonds. These atomic scale defects in diamonds exhibit unique quantum properties that are being explored for use in quantum sensing, computing, bioimaging, and even cryptography. So, what exactly is an MV center? MV centers are point defects in a diamond's crystal structure, where a nitrogen atom replaces a carbon atom and an adjacent vacancy is left unoccupied. These defects can trap electrons, make them highly sensitive to external fields, and useful for a wide range of quantum technologies. They are formed naturally or through ion implantation and annealing. They display for fluorescence when excited by green laser light, and they also have a unique spin dependent photoluminescence that makes them useful for quantum applications. What makes NV centers so special? Their quantum properties include an optical readout, which means NV centers emit red fluorescence under laser excitation, which varies depending on their spin state. They also have a long coherence time, which means NV sensors maintain quantum coherence even at room temperature, unlike many other quantum systems. And lastly, they have sensitivity to magnet and electric fields. Because their spin states are influenced by external perturbations, they function as atomic scale quantum sensors.
Quantum computing with NV centers uses tiny defects in a diamond called nitrogen vacancy centers to store and process information using the rules of quantum mechanics. An NV center is formed when one carbon in a diamond is replaced by a nitrogen, and the neighborhood spot is empty. So the special structure acts as a qubit. That's the quantum version of a regular computer bit. Unlike a regular bit that is only 0 or 1, a qubit can be both at the same time, hence the superposition that was mentioned in the last slide. It can also be linked to other qubits through entanglement. What makes NV centers exciting is that they're stable at room temperature and they have long coherence times and high precision control. So they can be controlled with lasers and microwaves, and their quantum state can be read by measuring light that they give off. These features make them useful for building quantum computers so small that enables secure communication and for quantum sensors that can detect tiny magnetic fields or temperature changes. There are definitely many challenges that make NV centers work together. The potential to use diamond as a platform for future of computing is both practical and incredibly promising. Um, However, making these envy centers that work is very hard, and getting them to work with each other is also very tricky. In order to set it up, which is initialization, you have to shine a green laser on the NV center to get it ready. That's to prepare the NV center. And then the second step, manipulation, is to control it using microwaves to flip or change the qubit center. And the third step, readout, is to shine the laser again and watch how much red light it gives off to figure out the answer. All in all, it is a stable and reliable tool for early stage quantum computers. Quantum sensing is a way of using powerful rules of quantum physics to measure things like time, temperature, magnetic fields, or tiny movements with extreme precision. Quantum sensors can detect things that are so small or subtle that regular tools miss them. They use quantum properties like superposition, that means being in two states at once, or entanglement, that's the instant connections between particles, to be extremely accurate. In medicine, quantum sensors can help detect diseases earlier by picking up sensors, faint signals in our body, and using super detailed brain scans um, that can detect um, the diseases. In navigation, planes and submarines also use quantum sensors. Even without a GPS, they can sense the gravity or tiny motions, tiny changes in motions. They can detect underground tunnels and minerals and early signs of an earthquake by measuring tiny changes in gravity or magnetic fields. Scientists also use them to study mysterious stuff like dark matter and gravitational waves. Um, and in the environment, they can also help detect pollution or monitor climate change.
Let's focus on two especially promising applications: nanoscale MRI and intracellular thermometry. First, nanoscale MRI. Unlike conventional MRI that images large scale tissue structures, NV centers enable magnetic resonance imaging at the nanoscale, allowing us to visualize single molecules or even individual proteins. This is made possible by the NV center's sensitivity to tiny magnetic fields. These sensors can detect the magnetic resonance signals of nuclear spins in molecules positioned just a few nanometers away. Importantly, this works at room temperature, without the need for labeling with contrast agents. This means researchers can observe biological systems in their natural state, which is incredibly valuable for studying dynamic processes like protein folding, drug interactions, or molecular diffusion. This application has the potential to bridge the gap between atomic resolution methods like cryo-EM and traditional imaging tools used in cell biology. Second, intracellular thermometry. NV centers can also act as quantum thermometers, using their spin state response to temperature changes. This allows for real-time temperature measurements within individual living cells, with sensitivity down to fractions of a degree. Why does this matter? Local temperature variations in cells can signal critical biological events like metabolic activity, inflammation, or apoptosis. Even more exciting, this can be applied in theranostics. For example, monitoring the localized heating effect of cancer therapies like photothermal or magnetic hyperthermia treatment. It could also enable precise heat triggered drug release, giving clinicians tight control over when and where a drug becomes active. What makes these applications truly impactful is that diamond nanoparticles are biocompatible and non toxic, meaning they can be used safely in live cells and even animal models. Now let's explore how nitrogen vacancy centers in diamond are being used in the field of quantum security and cryptography. These atomic scale defects not only have remarkable sensing capabilities, but also serve as powerful tools for securing information at the quantum level. Let's focus on two of the most promising applications: quantum key distribution, or QKD, and physical unclonable functions, or PUFs. First, quantum key distribution. QKD enables the secure exchange of cryptographic keys by harnessing the laws of quantum mechanics. NV centers in diamond are ideal for this because they can act as reliable room temperature single photon sources. These photons are used to encode the key bits during transmission. What makes QKD fundamentally secure is the no cloning theorem. It's physically impossible to perfectly copy a quantum state. So, if an eavesdropper tries to intercept or measure the photons, they inevitably disturb them, revealing their presence. This allows two parties to detect tampering and discard compromised keys before any data is encrypted. Researchers are already working on integrating NV based QKD into fiber optic and satellite systems, paving the way for global scale, unbreakable communication networks. Second, physical unclonable functions. PUFs use the intrinsic randomness in a material structure to create a kind of hardware fingerprint. In diamond, The naturally random spatial distribution of NV centers can be used to generate unique identifiers, ones that are virtually impossible to duplicate or forge. Unlike digital keys stored in memory, PUFs exist physically in the material and cannot be copied, even with complete access. This has exciting implications for device authentication, anti counterfeiting, and secure hardware for critical infrastructure or defense. Because NV centers are stable and non volatile, these systems can be used across a wide range of conditions, including extreme temperatures or radiation heavy environments. Together, these applications show how NV centers are helping to secure the future of digital and quantum communication, combining physics, material science, and information security in truly innovative ways.
Let's take a look at some industrial and engineering applications of NV centers. First, NV centers can detect extremely small magnetic fields with high sensitivity. This makes them incredibly useful for navigation in environments where GPS isn't available, such as underground, underwater, or even in space. These capabilities open up use in cases such as autonomous vehicles, defense systems, and resource exploration like mining. Another application is in gyroscopes. NV based gyroscopes use quantum interference to detect rotation with extraordinary precision. These could one day replace or enhance traditional fiber optic gyroscopes, offering better accuracy and reliability. The key benefit here is improved navigation in GPS denied environments, which is critical for aerospace, space missions, and advanced aviation systems. As we look ahead, NV Center technology is poised to make exciting advancements in several areas. First, real time and high precision measurements. Future NV sensors will offer faster data processing and improved sensitivity, which means we'll be able to use them for responsive diagnostics in healthcare and dynamic sensing in real world environments. Next, we have portable and wearable applications. Researchers are working on integrating NV sensors into compact, field ready devices, including medical wearable and handheld tools, which would expand their use far beyond the lab and into sectors like aerospace and industry. Another major prospect is integrating with other quantum technologies. By combining NV centers with quantum processors or communication systems, we can enhance the capabilities of quantum computing in secure networks. Finally, NV sensors can play a big role in automation and smart systems. Embedding them into AI driven or robotic platforms could improve smart manufacturing, enable autonomous navigation, and support next generation industrial systems. While NV centers show great promise, there are still some key challenges to overcome. First, technological barriers. NV sensors rely on highly specialized diamond materials and precise engineering. This complexity makes it difficult to integrate them into everyday consumer devices like smartphones or wearables. Second, there's the issue of cost and accessibility. Right now, mass producing NV based devices is expensive. For this technology to become widely available, we'll need new, scalable manufacturing techniques and more affordable materials. Addressing these challenges is essential to moving NV technology from the lab into everyday life. To wrap up, here's a quick recap of the key applications of NV centers. Quantum sensing. NV centers can detect magnetic, electric, and pressure fields with extreme precision. This is useful in fields like healthcare, material sciences, and navigation. Quantum computing. They act as quantum bits or qubits for storing and processing quantum information. Bioimaging and medical monitoring. NV centers enable high resolution imaging and can monitor cellular activity in real time, making them valuable in medical diagnostics. Security and cryptography. They support secure quantum communication and help generate truly random numbers for encryption. And finally, industrial engineering. NV based magnetometers and gyroscopes are being developed for advanced navigation systems in aerospace and defense.
These applications show just how versatile and impactful NV technology can be across multiple industries. As we look to the future of NV technology, several exciting developments are on the horizon. Firstly, we're seeing progress in miniaturization with efforts to shrink NV sensors for use in smart devices, wearables, and mobile tech, bringing quantum sensing directly to consumers. Next is real time processing. Faster, more accurate data analysis will support applications like continuous health monitoring and on the go environmental sensing. Then there's scalability and commercial use. Making NV technology more affordable and easier to produce will be key to its wider adoption in both industry and consumer markets. Lastly, quantum integration. NV centers are expected to play a major role in future quantum systems, combining with quantum processors and networks for advanced computing and secure communications. All in all, NV centers and Diamond are one of the most versatile tools in quantum technology today. From healthcare to aerospace, they hold the potential to transform how we sense, compute, and communicate. The road ahead is full of challenges, but also full of incredible possibilities.